Something happened to Voyager 2 that nobody prepared you for. Not the launch, not the journey, not the decades of silence as it sailed past planets and moons and the last edge of everything we call home. What happened is this: a spacecraft that left Earth 49 years ago on a mission that was supposed to last 5 years is still alive, still transmitting, still sending data back from a place so far beyond our solar system that the signal takes nearly 20 hours just to reach us. And what it is telling us right now is rewriting the rules of the universe. Nobody's talking about this loudly enough. There's a number that should stop you cold, not a political number, not an economic figure, a distance, 13 billion miles. That is how far Voyager 2 currently sits from the surface of the Earth. 13 billion miles of empty, freezing, radiation-soaked space between a machine built in the 1970s and the people still listening to it. Voyager 2 is roughly 21.35 billion kilometers, approximately 13 billion miles away from Earth, while its twin, Voyager 1, is about 25.40 billion kilometers away. And yet, against every reasonable expectation of engineering, physics, and time, both spacecraft are still transmitting, still operational, still doing science in a region of space that no other active mission in human history has ever directly explored. The instruments aboard Voyager 2 are not just surviving out there. They are measuring things that contradict our models of how the universe works at its largest scales. They are sending back readings from a region so remote and so poorly understood that every single data point they return represents something humanity has never directly measured before. And in August 2026, just days ago, a team of engineers at NASA's Jet Propulsion Laboratory pulled off something that the scientific community is describing in terms that rarely appear in press releases. Something they called, with deliberate and dramatic weight, the Big Bang. Think about what it means to name an engineering procedure after the origin of the universe. Engineers at NASA's Jet Propulsion Laboratory announced on August 4th that they had successfully completed a delicate power management procedure aboard Voyager 2, a simultaneous swap of multiple power-consuming devices for lower power alternatives, internally nicknamed the Big Bang, that will keep all three of the spacecraft's remaining science instruments alive for at least one additional year. Without the maneuver, the mission would have been forced to shut off another instrument before the end of 2026, leaving humanity's only in situ sensor network in interstellar space with 2 instruments instead of 3, a loss that cannot be undone and cannot be replaced by any currently funded or planned mission. Read that final phrase again. A loss that cannot be undone and cannot be replaced by any currently funded or planned mission. NASA did not say that casually. That is a statement of irreversibility, of permanent civilizational consequence. Because the instruments aboard Voyager 2 are not merely scientific tools. They are the only eyes and ears humanity currently possesses in interstellar space. There is no backup. There is no substitute. There is no other spacecraft traveling to that region with replacement sensors. When Voyager 2's last instrument finally falls silent, humanity will go blind in the space between the stars for a generation, perhaps longer. And what those instruments are seeing right now is not what anyone expected. To understand why this matters so profoundly, you need to first understand where Voyager 2 actually is. Not the number, the geography. Because 13 billion miles sounds abstract until you understand the boundary it represents. Until recently, the space surrounding Voyager 2 was filled mostly with plasma flowing outward from the sun. This outflow, called the solar wind, creates a bubble, the heliosphere, that envelopes all the planets in our solar system. Every planet you have ever seen in a photograph, every moon, every asteroid, every piece of rock and ice and gas that orbits our star. All of it sits inside this bubble, the heliosphere, a vast magnetic and plasma envelope that the sun generates and maintains through the constant outpouring of its solar wind. Voyager 2 crossed the boundary of that bubble. It left the heliosphere behind. On November 5th, 2018, NASA's Voyager 2 became only the second spacecraft in history to leave the heliosphere, the protective bubble of particles and magnetic fields created by our sun, where the only other human-made object is its twin Voyager 1. That crossing was the moment that everything scientists thought they understood about the outer edge of our solar system was simultaneously confirmed in some ways and shattered in others. Because when Voyager 2's instruments reported back what they encountered at the Heliopause, the precise boundary where the solar wind ends and interstellar space begins, the data told a story that the models had not predicted. When Voyager 2 exited the heliosphere, scientists announced that its 2 energetic particle detectors noticed dramatic changes. The rate of heliospheric particles detected by the instruments plummeted, while the rate of cosmic rays increased dramatically and remained high. The changes confirmed that the probe had entered a new region of space. That much matched the predictions. But then the magnetic field data arrived. And the magnetic field data did something that none of the theoretical frameworks had prepared anyone for. An observation by Voyager 2's magnetic field instrument confirmed a surprising result from Voyager 1. The magnetic field in the region just beyond the Heliopause is parallel to the magnetic field inside the Heliosphere. The magnetic field did not change direction when Voyager 2 crossed into interstellar space. Scientists had predicted it would. Every model said it should. It didn't. According to informed sources in the astrophysics community, this is not a minor discrepancy. The direction of the magnetic field at the Heliopause boundary is foundational to our understanding of how the heliosphere interacts with the surrounding interstellar medium, the vast cloud of gas, dust, plasma, and radiation that fills the space between stars. If the field directions match on both sides of the boundary, it suggests something about the structure and geometry of our solar system's outer shell that the current best models fundamentally fail to account for. It means the shape of the heliosphere, which some models describe as a comet-like teardrop, others as a more spherical bubble, may be something entirely different from what we have been drawing in textbooks for decades. What most people are not seeing is that this is not just about Voyager. It is about what Voyager is telling us about the architecture of our entire solar system, and what that architecture means for Earth. Here is why that matters in a way that goes beyond academic interest. Voyager 1 discovered that the heliosphere protects Earth and the other planets from more than 70% of that radiation. Cosmic rays, those high-energy particles accelerated by exploding stars across the galaxy that would otherwise bombard every living organism on this planet with lethal regularity. The heliosphere is not just a boundary marker. It is a shield. It is the invisible electromagnetic fortress that makes complex life on Earth physically possible. And right now, for the first time in history, we have a spacecraft on the other side of that shield, measuring exactly how it works, exactly where it fails, and exactly what gets through. The data it returns does not just satisfy scientific curiosity. It tells us how fragile our protection actually is. But here is where it gets worse. Because while Voyager 2 is delivering irreplaceable measurements from outside the heliosphere, it is doing so while dying. Slowly, instrument by instrument, in the unimaginable cold of deep interstellar space, the spacecraft is losing power. The Big Bang procedure involved turning off 2 dedicated heaters and a digital tape recorder, and turning on lower power alternative heaters and another heat-producing device to keep the spacecraft warm enough to operate in interstellar space. At about 2.7 Kelvin, that is approximately negative 270 degrees Celsius, just barely above absolute zero, the coldest temperature that physics permits to exist. In that environment, every wire, every circuit board, every instrument package aboard a spacecraft built using 1970s technology is operating at the absolute outer limit of its design tolerance. And it has been doing so for years. To keep Voyager 2 continuing its journey and collecting invaluable data, NASA recently made a daring fix dubbed the Big Bang. In July, scientists turned off some of the probe's devices, namely heaters, and turned on substitutes that require less energy. The nickname captures the scale of what engineers were attempting. All the changes had to happen simultaneously in a single coordinated command sequence because making the swap in stages risked catastrophic thermal instability aboard a spacecraft where engineers cannot physically intervene, cannot send a repair crew, and whose response to any command takes nearly 20 hours to receive. It takes nearly 20 hours for a command to reach Voyager 2, and then the team has to wait the same amount of time to receive a response before moving forward. That is a 40-hour feedback loop. 40 hours of uncertainty between sending a command and knowing whether the spacecraft survived it. Think about what that means for the engineers who designed and executed this procedure. They wrote the commands, they sent them into the void, and then they waited nearly 2 days of not knowing whether the most distant active spacecraft in human history was still alive or had gone permanently dark. This is the reality of operating at the frontier. Not the cinematic version, not the glossy press release version, but the actual human experience of managing irreplaceable hardware across a distance that makes the concept of real-time control physically impossible. The Big Bang worked. The procedure kept all 3 of the spacecraft's remaining science instruments alive for at least 1 additional year. But NASA has been deliberate and careful in how it frames this victory because the underlying mathematics of Voyager 2's power situation have not changed. NASA has been careful not to frame this as a permanent fix. The radioisotope thermoelectric generators that power both Voyager spacecraft have been losing approximately 4 watts of power per year since launch. After nearly 50 years of continuous operation, power margins have shrunk to razor-thin tolerances. Every year from this point forward, the engineering team faces the same calculation: which instrument to sacrifice next, and how much longer the remaining instruments can be kept operational before the physics become impossible to negotiate. And what are those remaining instruments measuring that is worth all of this extraordinary effort? The magnetometer measures the interstellar magnetic field directly. Nothing else humanity owns is out there to do this. The The plasma wave subsystem picks up electromagnetic waves in the thin ionized gas around the spacecraft, which reveals how dense that gas is and how it behaves. The cosmic ray subsystem counts high-energy particles arriving from the galaxy and from the sun. These three instruments are not redundant. They are not measuring the same thing from different angles. Each one is capturing a completely distinct physical phenomenon, and together they are building a composite picture of interstellar space that no telescope, no satellite, no Earth-based instrument can replicate. Because there is a fundamental and unbridgeable difference between observing the interstellar medium from inside the heliosphere and actually being in it, Voyager 2 is in it. Every measurement it returns is a direct sample, the equivalent of being inside the ocean rather than studying it from the shore. The real story is that the interstellar medium is nothing like what we modeled it to be. Just beyond the Heliopause, Voyager 2 discovered a boundary layer in which low-energy particles streamed outward along the magnetic field, and cosmic ray intensities were only 90% of those further out. A boundary layer, a transitional zone between the heliosphere and true interstellar space that the models had not predicted, and that still lacks a complete theoretical explanation. This region, neither fully inside our solar system nor fully outside it, appears to be a complex mixing zone where particles from two fundamentally different environments interact, collide, and exchange energy in ways that physicists are still working to characterize. Like its twin Voyager 1, Voyager 2 appears to be in a perturbed transitional region just beyond the heliosphere, not yet in undisturbed interstellar space. What that means is staggering. Even after crossing the Heliopause, after traveling further than any human-made object in history, Voyager 2 is still in the influence zone of the Sun. The heliosphere's reach extends further than anyone calculated. The Sun's gravitational and electromagnetic footprint on the surrounding interstellar environment is larger, messier, and more complicated than the clean theoretical boundary in the textbooks. And as Voyager 2 pushes deeper into this transitional region, measuring how the influence gradually fades and the true interstellar environment begins to assert itself, the data it returns is updating the foundational models of how stars interact with their surrounding space. Every star in the Milky Way has a heliosphere equivalent, a stellar sphere carved out by its own solar wind. Understanding how our heliosphere behaves at its boundary, how it shapes the local interstellar medium, how the transition zone works, this is not just information about our Sun. This is a template for understanding the local environment of every stellar system in the galaxy. And the implications for the search for habitable worlds around other stars are direct and profound. The protective shielding our heliosphere provides may be a critical variable in whether any given planet can sustain complex life, a variable that scientists have barely begun to factor into their calculations about where life might exist beyond Earth. But here is where the story takes a turn that most people are completely unprepared for. Cosmic rays from outside the solar system contain particles accelerated by exploding stars, supernovae, some of which occurred millions of years ago in the Milky Way galaxy. Those cosmic rays are the galactic background radiation of a violent universe, the echoes of stellar deaths spread across time and space, slamming into the heliosphere's outer boundary at near-light speeds, partially deflected, partially absorbed, partially allowed through to reach our planets. The 30% that gets through the heliosphere, the fraction that Voyager 1 confirmed passes the shield, is the cosmic ray flux that Earth's magnetic field, atmosphere, and biology have adapted to over billions of years. But that percentage is not fixed. It is not stable. It depends entirely on the health and geometry of the heliosphere itself, which fluctuates with the Sun's activity cycles. What Voyager 2's instruments are measuring in real time is exactly how that shielding varies with position in the galaxy, how much the interstellar cosmic ray environment changes as you move further from the Heliopause into the deeper interstellar medium. For nearly half a century, the instrument measured charged particles like ions, electrons, and cosmic rays coming from our solar system, as well as the Milky Way galaxy more broadly. The measurements have provided unprecedented data about regions of varying density beyond the heliosphere. This data is the first and only direct measurement of the interstellar cosmic ray environment from inside it. It is telling scientists things about the local galactic neighborhood, the density, composition, and energy spectrum of particles that fill the space between stars, that no other observation method can provide. And the picture that is emerging is one of a solar system more precisely tuned to the requirements of complex life than anyone fully appreciated before Voyager crossed the Heliopause. According to informed sources in the astrobiology and heliophysics communities, the combination of factors that creates Earth's habitability is not simply a matter of orbital distance from the Sun. It includes the heliosphere's protection from galactic cosmic rays. It includes the specific magnetic field geometry at the Heliopause boundary. It includes the density and composition of the interstellar medium through which the entire solar system is currently sailing at 25 kilometers per second. The solar system is not stationary in the galaxy. It is moving, and the properties of the interstellar environment it moves through vary. Voyager 2's data suggests that the current local interstellar environment, the specific region of interstellar space that our heliosphere is currently carving through, may be unusually quiet, unusually low density, and unusually favorable for maintaining a robust heliospheric shield. In other words, the conditions right now may be unusually good. And that raises the question of what happens when they're not. The current measurements indicate that the interstellar density has increased further from the value it had outside the Heliopause, but no one knows what will happen next. If the solar system moves into a denser region of the interstellar medium, a molecular cloud, a region disturbed by a nearby supernova, a zone of elevated cosmic ray flux, the heliosphere compresses. Its shielding geometry changes. The percentage of cosmic rays that penetrate to the inner solar system increases. The radiation environment at Earth's surface shifts. And over geological timescales, those shifts have consequences for biology, for climate, for the pace and direction of evolutionary change. Voyager 2 is, among other things, the first instrument that can tell us what the solar system is sailing toward, what kind of interstellar environment lies ahead, and whether the conditions that have sheltered complex life on Earth for 500 million years are likely to continue. This is not speculation. This is the scientific program that NASA's Jet Propulsion Laboratory has committed engineering heroism to keep alive. Each additional measurement from Voyager 2 adds to humanity's understanding of the region beyond the solar system. The spacecraft continues providing information from a location that no telescope or Earth-based instrument can directly reproduce. That is the key phrase. It cannot be directly reproduced. There's no substitute for being there. You cannot model your way to this data. You cannot observe it from a distance. The physics of interstellar space can only be measured by an object that is in interstellar space. And right now, the only objects humanity has ever placed there are 2 spacecraft launched in 1977 with technology that predates the personal computer, the internet, and the smartphones that now carry more computational power than the entire JPL mission control system of the time. And they are still working, still transmitting, still teaching us things about the universe that we could not know any other way. Both Voyager 1 and 2 have spent almost 49 years soaring through space. In the process, they have traveled farther than any other human-made objects have ever gone before. Initially intended to provide never-before-seen glimpses of the outer planets, they have surprised researchers by continuing to send back remarkable data while sailing further into the unknown. The original mission lasted 5 years. What followed has lasted nearly half a century, and the discoveries have not slowed. If anything, the deeper Voyager 2 travels into the interstellar medium, the more the data diverges from prediction, and the more valuable each individual measurement becomes. On November 18th, 2026, Voyager 1 will officially have traveled 1 light day from Earth, a record distance that many of the spacecraft's designers never imagined possible, and one that likely will not be surpassed anytime soon. 1 light day. The distance that light itself, traveling at 300,000 kilometers per second, covers in an entire day. A human-made object built with mid-20th century engineering will have traveled that far. And Voyager 2, on its own trajectory, continues to extend its own record daily, moving further from Earth every second, measuring as it goes, returning data that accumulates into the most comprehensive picture of the outer solar system and local interstellar space that humanity has ever possessed. But the question that hangs over all of this, the one that the Big Bang maneuver has pushed slightly further into the future without eliminating, is what happens when the last instrument finally goes dark. The future of Voyager 2 will depend on how engineers manage its remaining power and spacecraft systems. As the mission progresses, NASA will continue evaluating which instruments can remain active and how scientific operations can be maintained. These are the words of an organization that knows the end is approaching and is managing it with the same careful discipline. They have brought to every challenge in this mission's extraordinary history. The Big Bang bought 1 more year. The next engineering innovation might buy another year beyond that. But the physics are what they are. The plutonium in the radioisotope generators decays at a rate that no human ingenuity can alter. The power curve slopes downward, and at some point, it reaches a threshold below which the instruments cannot function. When that happens, it will be among the most significant silences in the history of science. A data stream that has run continuously for nearly 5 decades, returning measurements from the edge and then the beyond of our solar system, will simply stop. The last signal will travel its 20-hour journey to Earth. The last data point will be processed, and then there will be nothing. No replacement mission is currently funded. No successor probe is scheduled to reach the Heliopause within the lifetime of any scientist currently working on Voyager. The interstellar medium will go dark to human instruments for a generation. And what we currently know suggests that we have only barely begun to understand what is out there. The magnetic field anomalies at the Heliopause remain unexplained. The boundary layer's particle dynamics are only partially characterized. The precise shape of the heliosphere, whether it is a comet tail, a sphere, something else entirely, is still debated among theorists who are all working from the same limited Voyager dataset because it is the only dataset that exists. The cosmic ray flux in the deeper interstellar medium, beyond the transitional zone where Voyager 2 currently operates, has never been directly measured. The interstellar magnetic field's full three-dimensional structure is known only along two narrow tracks, the trajectories of Voyager 1 and Voyager 2, in a three-dimensional ocean of space that spans light years in every direction. The real story is that Voyager 2's greatest revelations may still be ahead of it, and the clock is running down. Everything humanity has learned about interstellar space has come from two spacecraft launched before most of the scientists currently analyzing their data were born. Every model of the heliosphere, every calculation of cosmic ray shielding, every estimate of the local interstellar environment. All of it rests on a foundation of measurements from instruments that were designed with slide rules and assembled by hand. And those instruments, improbably, miraculously, stubbornly, continue to function at the furthest edge of the possible, returning data that keeps revising the textbooks. The Big Bang was not just an engineering achievement. It was a declaration, a statement from a team of human beings that, as long as there is a signal coming from 13 billion miles away, we will find a way to keep receiving it. We will trade one system for another, sacrifice one instrument to save three, endure 40 hours of silence waiting for confirmation from the void. Because what Voyager 2 is measuring out there matters more than the difficulty of keeping it alive. What it is measuring is the boundary of our world, not Earth's boundary, not the solar system's visible boundary of planets and moons and rings. The true boundary, the edge of the sun's influence, the place where our star's dominance over local space finally yields to the vast interstellar environment of the galaxy itself. Voyager 2 crossed that boundary. It is living on the other side of it. And every day it survives, it brings back something from a place no other human-made object has ever been. The universe beyond our solar system is not empty. It is not quiet. It is filled with magnetic fields and plasma density variations and cosmic ray fluxes and phenomena that our models are only beginning to describe. And it is measuring us as much as we are measuring it. The heliosphere pushes outward. The interstellar medium pushes back. And in the dynamic collision zone between them, the conditions that make Earth habitable are either reinforced or undermined by factors that, until Voyager crossed the Heliopause, we could not directly observe. Now we can, for a little while longer. One more year, bought by an engineering procedure nicknamed after the beginning of the universe. What comes after that year? What happens when the cosmic ray subsystem finally loses the last fraction of a watt it needs to operate? What changes in our understanding when the interstellar magnetic field measurements stop arriving, and we are left to extrapolate from the final data points of a sensor that traveled further than any human artifact in history? The answer is that we do not know. And that uncertainty, the uncertainty of a species that has just barely managed to reach the edge of its own cosmic home and glimpsed what lies beyond, only to watch its one and only scout slowly run out of power, is perhaps the most important truth that Voyager 2 has delivered in 49 years of service. We have barely left, and already we are almost out of eyes to see with. The silence, when it comes, will be the loudest thing humanity has ever not heard.